We have now come to the fourth and final use case that we're going to explore in this video series, the sign test for match pair differences. This is an important case because it involves looking at a control versus a treatment and measuring the effect of the treatment. If you have watched this entire video series, the setup is one that you're familiar with. We match participants on an extraneous variable. The extraneous variable, of course, needs to be a variable that is related to the outcome measure in the study. We then randomly select which member of each pair will go into the treatment and which will go into the control, thus resulting in participants in a treatment condition who are closely matched to those in a control condition on important extraneous variables. Let's look at the design and conditions that we will need in order to conduct the sign test. The pairs of participants are independently selected, with each pair defined by a match on a relevant extraneous variable. Obviously, because of this match, the participants are not independent of one another within a pair, but the pairs must be independent of one another. This can be achieved by randomly selecting participants, matching them into pairs, and then randomizing to two conditions, a treatment and a control. With this particular use of the sign test, the participants are measured with quantitative measurement, either interval or ratio, after the intervention. That is because we need to calculate difference scores for each pair. The amount of difference for each pair will be an indication of how effective the treatment was within that pair. The population medians of the difference scores must be the same across pairs. Think about that a moment. At first, this may seem like a strong condition that would be difficult to achieve. However, if you are selecting participants from the same population, then you are only dealing with one population median, even for difference scores. Given that that's always the case when we select from a single population, the obvious question is, why did I include this in the list of conditions? I'm glad you asked. It is because participant pairs can be selected from different populations as long as they have the same median. That's a unique characteristic of this particular test. You could potentially purposefully select participants from different populations to determine if the treatment is effective across these populations. Now that raises another consideration. If you're selecting from different populations based upon some extraneous variable, and that extraneous variable interacts with the treatment, you would not expect that the treatment would have the same effectiveness from one population to another, and therefore the medians of the difference scores would not be the same across the pairs. Except in one situation, and that is if the treatment has no effect. In that case, the median of difference scores is going to be 0, regardless of which population you're selecting from. So in practical terms, if you want to have the full array of statistical inference tools at your disposal, you will select participant pairs from the same population. If, however, your primary interest is in whether the treatment has any effect at all across a variety of populations, you can select participant pairs from the different populations and test the single null hypothesis that the median of difference scores is 0. As we conduct our study, we'll need to measure each participant within the treatment condition and each participant within the control condition. And then in each pair, we subtract the measured value of the control participant from the measured value of the treatment participant, or vice versa. The result is that we'll end up with a difference score that represents the effectiveness of the treatment within each pair. If higher values represent better outcomes, and we have subtracted the control participant score from the treatment participant score, then of course positive values will indicate a positive effect of the treatment, and negative values will indicate a negative effect. We're talking about the sign test here, so we are focusing on the number of plus signs that we obtain, although now we can additionally calculate a median of the difference scores, and that median of the difference scores would be an estimate of the treatment effect. This is analogous to when we conduct a one-sample match pair test in the parametric world, and we obtain an estimate of the mean of the difference scores. Here we're obtaining an estimate of the median of the difference scores. As you know, if the distributions are symmetrical, the mean and the median will be the same. If they're not symmetrical, the median is actually a better estimate of that treatment effect. Moving on to inference, let's look at the hypothesis test. The most obvious null hypothesis, and the one that would allow us to draw our participants from the same or different populations, is that the median of the different scores equals 0. That is, the treatment has no effect. And the alternative is that the median of the different scores is greater than 0. Let's suppose we're going to use an alpha of 0.05, and in the example that we've been looking at, the number of positive signs is 6. If we look at the probability table for the binomial distribution, we determine that the probability of having 6 or more plus signs, if the null hypothesis is true, is 0.062. Therefore, our p-value is 0.062, and we retain the null hypothesis and cannot conclude with 95% confidence that there is a treatment effect with this particular set of 7 difference scores. Here are those difference scores, and let's see now how we can use these in order to construct a confidence interval. We already know that 0 is going to be in the confidence interval because we retain the null hypothesis about the median difference score being 0. If you look again at the binomial probability table, you see that the only time we will reject the null hypothesis is when the number of plus signs is 7. Looking again at these values, think about how we could adjust these scores so that all of them are positive. Note that if the median difference is -2, that is, I adjust the scores by subtracting -2 from every value, the one negative score that we have in this set of scores would become 0. That is still not positive, but what it clues me into is if I had used any value even further in the negative direction, like -2.1, and subtracted that, I would indeed end up with all positive scores. Therefore, the median of the difference scores is greater than -2, so the estimate of our treatment effect tells us that the treatment may not work, that is, 0 may be the median difference scores. Things may get worse, but if they do, the distribution will shift only by 2 points in the negative direction, and things may get better, perhaps even substantially better. Obviously, with these 7 scores and with the differences we found, we do not know yet whether the treatment is even effective, and if it is effective, how much. In the next round of my research, I would seek to do a larger study.